Hello, everybody. So it's Wednesday, and on Friday you have your exam. So look for that to be released on Blackboard. The logistics will be similar to the last time around. And so what I'm going to talk about today is not going to be on the exam, but it is very much related to the material we have been covering. And so what I would like to hold forth about today will be the chemistry of nitriles. Remember, these nitriles are organic cyanides, right? They have an organic group and then these carbon-nitrogen triple bond of the nitrile group. Now, ordinarily, when we're thinking about cyanide, if we ever think about it at all, we're probably not in a very happy place because we know that cyanide is a violent poison. It is a favorite of suicides everywhere. Cyanide is the gas that is administered in the gas chamber used to execute death row inmates. So usually when we're thinking about cyanide, we're not in a real happy place. However, cyanide is an extremely useful component of many laboratory organic reactions, and how it fits into what we have been studying is that cyanide and nitrile chemistry is used to create amino acids in the laboratory. Obviously, this is not how amino acids are created in a physiological system, but in a laboratory, if you want to create an amino acid, well, one way to do it is to take advantage of the chemistry of cyanide. So that's why it fits in with what we've been talking about. Okay, so this is called the Strecker synthesis of alpha amino acids. All right, and so what I'd like to talk to you about in today's lecture will be the detailed consideration of this reaction. All right, so in the Strecker synthesis, you take an aldehyde. So this is an aldehyde. And it's a two-step reaction. In the first step, the aldehyde reacts with something called ammonium cyanide, right? And we'll have a lot to say about ammonium cyanide in a little bit. So that's will be the first step. And in the second step, it's acid and water. Remember H3O+. This is equivalent to saying H+ and water. And heat, and the product of this two-step reaction turns out to be an alpha amino acid. And so this is a versatile way of making an amino acid because, you know, this is the R group. This could be any one of 20 different groups of the groups that are coded for, the amino acids that are coded for by DNA. So you can just play around with whatever this R group is and come up with whatever amino acid you want to make. So this is a nice way. Well, I don't know how nice it is, but this is a way of making an amino acid in the laboratory. So this guy here, the aldehyde carbonyl, I'm going to put a little dot on him. He turns out to be the alpha carbon of the alpha amino acid. The nitrogen in the alpha amino acid this came from the ammonium ion in ammonium cyanide and the carboxylic acid carbon of the alpha amino acid, this guy here, he came from the cyanide of the ammonium cyanide. Okay, so this is a laboratory synthesis of amino acids. Just by playing around with this R group, you can get a lot of amino acids, and you can even make amino acids that are not coded for by DNA, and there are plenty of those. And some of them have some very interesting properties. Okay, so let's talk about the Strecker synthesis of the alpha amino acid. First of all, we've known for a very long time now that the carbonyl carbon of an aldehyde or a ketone or an ester or anything else, we've known that that is an electrophile. It is attacked by nucleophiles. So if we look at cyanide itself, we see that, well, cyanide's a nucleophile. I see that electron pair on this carbon atom. I see this negative charge. That's a nucleophile. So that cyanide is a nucleophile. The carbonyl carbon of the aldehyde or a ketone is an electrophile. We're going to get a nucleophile attacking an electrophile. Now, in the laboratory, we also would want to have some HCN around. Okay, and so what is going to happen here is that the cyanide attacks the carbonyl carbon, and we get an intermediate that looks like this. Okay, so that's just the nucleophile attacking the electrophile. And then that O minus, the negative charge on that O minus is put out by HCN. So now HCN gets involved, and this O minus picks off a proton from HCN. And we end up with this kind of compound. This reaction is simply illustrating that and reminding you that the aldehyde or ketone carbonyl is an electrophile, cyanide's a nucleophile. And so when the nucleophile and the electrophile get together, we get this kind of compound. This is called a cyanohydrin. Okay, so this step isn't part of the Strecker synthesis, but it is an important reaction to know about, simply because it just will remind us about a nucleophile attacking with an electrophile. Now, these cyanohydrins, these are pretty interesting compounds in their own right, and in fact, they are biological. They are compounds that are found in biological systems. You have inside your gut enzymes called nitrile lyases, and what a nitrile lyase does is it clips the CN group off of molecules. And so if you ingest a cyanohydrin, or if you ingest an organic molecule that has the nitrile functionality on it, these enzymes, the nitrile lyases, get to work and they clip the CN minus off. And pretty soon inside your bloodstream, inside your stomach, you have cyanide running around. Well, that's not very good, because cyanide is a poison. Okay, so let me try to show you some pretty pictures here. All right, so this is mandilonitrile. It's a cyanohydrin. I see that CN minus attack. This used to be a carbonyl here. This is the defense mechanism of the African millipede, so that when this millipede is attacked by a mongoose or a jaguarundi or a kudamandi or whatever it is there in Africa that would like to eat this big juicy uh, millipede, this millipede inside its body has this cyanohydrin. And when that mongoose or whatever it is eats this millipede, the mongoose has nitrile liases in there that are going to clip the cyanide off. And pretty soon that mongoose, as a result of eating this millipede, gets poisoned. So if that mongoose has any sense, next time it sees one of these big juicy worm like millipedes, it's not going to attack one. It's not going to kill one. It's not going to eat one. Because maybe if it has any sense, it remember it got sick last time. So this is how the species as a whole would survive these attacks of predation. The millipede that got eaten, he's dead. He's gone now. But the species as a whole persists. Okay, so that's very well and good. And I know that I don't want to eat stuff with cyanide. Why would anyone ever eat anything with cyanide in it because it's a poison? Well, it turns out that people are eating stuff with cyanide in it all the time. Let me bring you back to your world. Maybe a lot of you are interested in dietetics and in nutrition. Okay, so here is an organic cyanide. This is found in the cassava. This is cassava here that this little girl is carrying on her head. And in the Spanish-speaking countries, it's called yucca. So this is a compound that is in the roots of this cassava or yucca tuber. Unless the yucca or the cassava is thoroughly washed with lots and lots and lots of clean water, this organic cyanide will remain in the cassava. But you know what? About 2 or 3 billion people on this planet do not have access to unlimited quantities of clean water. So that where cassava is a staple food, I'm talking about sub-Saharan Africa and a lot of South America, where cassava is a staple food, people are running around with low-grade cyanide poisoning because the root cannot be thoroughly cleansed in water. They don't have water to do the kind of adequate job to rinse the cassava free of all of this linamarin. So they ingest the cassava, they ingest the yucca, it has the cyanide in it, the nitrile liases go to work, clip off the cyanide, and pretty soon this little girl, unless she has had access to unlimited amounts of clean water, is going to have cyanide poisoning. And there are about 2 billion people on this planet that have a chronic low-grade cyanide poisoning. So, if you're interested in dietetics and nutrition, maybe you would be interested in the dietetics and nutrition of people who don't have supermarkets and who don't live in rich countries where they have access to all kinds of food. Okay. So I want to be here. How do I get rid of all of you people? Yeah. Okay, so now with that introduction about the fact that cyanide is a nucleophile, we can turn to the structure synthesis per se. All right, so the star of the first step is this material called ammonium cyanide. And when ammonium cyanide dissolves in water, the ammonium cyanide breaks up into ammonium ion and into cyanide ion, right? Well, so this is just like if you were to take sodium chloride and dissolve it in water. This is a salt. Sodium chloride is a salt. If you were to take sodium chloride and dissolve it in water, it would break up into sodium ion plus and chloride minus, chloride ion minus. So it's the very same thing here. However, now I'm looking at this and I see, oh, this ammonium ion can function as an acid. And this cyanide ion here can function as a base. Well, it has that negative charge, and we've known for a long time that stuff that has negative charges on it, well, that is going to function as a base. So the ammonium ion does an acid-base reaction with the cyanide ion, and the ammonium ion trades a proton to the cyanide, and what is created there is ammonia and HCN. Now, looking at that famous table of pKa's, I can calculate the equilibrium constant for this acid-base reaction. Okay, so the ammonium ion, his pKa is 10, HCN, his pKa is 9. The equilibrium constant using that Henderson-Hasselbalch equation would be 9 minus 10 is equal to 10 to the minus 1 is equal to 0.1. Okay, so the equilibrium constant is less than 1, but it's not a whole lot less than 1, right? This equilibrium constant didn't come out to be 0.0000, 10 to the minus 9 or something like that. It's less than 1. That means that reactants are favored, but it's respectable. And so if you work out all of these numbers, what it turns out to be that in these solutions, 90% of the nitrogen is bound up as ammonium ion, and 10% is bound up as ammonia. So that's what this equilibrium constant of 0.1 means. Another thing this equilibrium constant means that 90% of the carbon is bound up as cyanide, and 10% of the carbon in there is bound up as HCN. So there's a respectable amount of NH3 there. There's a respectable amount of HCN in solutions of ammonium cyanide. So the bottom line is that solutions of ammonium cyanide have a good amount of ammonium ion, cyanide ion, ammonia, and HCN. And not only that, but because these pKa's of 10 and 9 indicate that these guys are not strong acids, solutions of ammonium cyanide are actually basic, so that you also have OH minus in there as well. Okay, so dissolving ammonium cyanide in water produces all of these, produces ammonium ion, cyanide ion, ammonia, HCN, and also OH minus. It's a complicated mixture of stuff. Okay, so that's what ammonium cyanide does. Now we can turn to that Strecker synthesis, or continue talking about that. So we have the aldehyde. We start out with this aldehyde. Start out with this aldehyde, and we add ammonium cyanide to it, and we know that ammonium cyanide has some NH3 in it. So down here in quotes, I'm going to put NH3. And what I mean by that is that we just talked about how a solution of ammonium cyanide produces some NH3. Okay, and so what we have here is the recipe for the imine, right? A primary amine and an aldehyde. These two get together to form an imine. Right? We're not going to go through the mechanism because we've done that plenty of times. Okay. So now so now this isn't a carbon oxygen double bond, right? It's not an aldehyde or a ketone anymore. It's an imine. This isn't a nitrogen. This isn't a carbon oxygen double bond. It's a carbon nitrogen double bond. But the chemistry of the carbon nitrogen double bond is frequently very similar to the chemistry of the carbon oxygen double bond, in that I can draw a resonance structure for the imine, in which I know that carbon is less electronegative than nitrogen. I know that nitrogen is sucking electrons away from the imine carbon, and so the imine carbon has a partial positive charge on it. The imine carbon can be attacked by nucleophiles, right? We've seen that over and over and over again, as especially in the reaction in which we have reversion of the imine to a primary amine and an aldehyde or ketone. And so now the HCN that is found in solutions of ammonium cyanide are going to get involved. So I'm going to put this in quotes again, HCN. We're not adding HCN. The HCN is coming from the ammonium cyanide. And so the H in HCN is going to protonate this negative charge, and the Cn minus of HCN that's a nucleophile. It's going to attack the electrophilic carbon. Okay, and so that's an intermediate. It's called an aminonitrile. It doesn't really matter what it's called, but that's what happens when an aldehyde is dissolved in a solution that has ammonium cyanide in it. We get this compound. Okay, so that's the end of step one of our Strecker synthesis. Now, to achieve the alpha amino acid, all we need to do is convert this CN to a carboxylic acid. And so we take this guy, react him with H3O plus, right? This is the end of step one. That's the end of step one. And now this is the second step of the Strecker synthesis. And what H3O plus and heat do is that they convert the nitrile, they convert the nitrile to a carboxylic acid. And so there's our alpha amino acid. So this is that lab preparation of the alpha amino acid. Okay, this chemistry here, this is new. So we want to talk about the mechanism and characteristics of this reaction here, the conversion of a nitrile to a carboxylic acid. All of this other stuff is pretty much old hat. We've seen all of this before. So let's concentrate now on this final step. Okay, so it's the nitrile being turned into a carboxylic acid. This is called acid hydrolysis of a cyanide to a carboxylic acid. Okay, the overall reaction is you take a organic nitrile. You take a nitrile, react that with 2 equivalents of water and H plus. So notice this time I didn't write the H plus over the arrow because in this reaction, H plus is not a catalyst. It is consumed stoichiometrically, right? It's not a catalyst is something that takes part in the reaction mechanism. It gets everything going at the beginning, but the last step, it will usually be spat out. Right? That's not what's happening here. So I didn't write H plus above the arrow. H plus is not a catalyst. And the product here is a carboxylic acid and the ammonium ion. Okay. And so this reaction happens whether Cn minus is involved in the Strecker synthesis or not. This is just a general reaction or hydrolysis of a nitrile to a carboxylic acid. How about let's try some product prediction. This guy plus water plus acid. Oh, we also need heat here. Plus heat, because this reaction doesn't happen all by itself. What's going to happen? Well, Cn minus is going to be converted to carboxylic acid. And this is the alpha amino acid valine. Okay, and how was this guy created using Strecker synthesis? Well, if you look at my comments a little bit earlier in the lecture, I pointed out that the alpha carbon of the alpha amino acid started out as an aldehyde carbon. The alpha amino group came from ammonium cyanide. The cyanide group came from ammonium cyanide as well. So this amino acid valine could have been created from this aldehyde. This plus ammonium cyanide gives you this, and then hydrolysis of the nitrile takes you on. That's step 2 of the Strecker synthesis, takes you on to valine. And so notice that I was able to come up with this amino acid just by playing around with whatever is the R group here on the aldehyde. Okay, so we want to talk about the mechanism of this acid hydrolysis of the nitrile. Okay, so I'm going to have to erase this because I'm going to need a lot of room. All right, so start out with the nitrile. And we have some acid, And so the first step of the mechanism, right, I'm talking about mechanism. First step of the mechanism is the protonation of the nitrile nitrogen. So this is new. We haven't seen this before. But I would like for you to compare the first step of what happens in many of the reactions that we have studied up to now, where the first step has always been protonation of the carbonyl oxygen. Right, the carbonyl oxygen has these unshared pairs of electrons that can grab a proton from the solution. Nitrogen has an unshared pair of electrons that can grab a proton from solution. So this is not really conceptually a totally new thing. It's just protonation of that nitrogen, similar to protonation of the carbonyl oxygen. All right, so now we have an intermediate that looks like this, right? Okay, and this guy we see that the nitrogen has that positive charge. It doesn't like to have a positive charge. It would rather be neutral or negative because nitrogen is pretty electronegative, right? We've said the very same thing about oxygen bazillions of times. A positively charged oxygen, that's not happy. It wants to lose the proton, it wants to become neutral, or it wants to become negative. So this nitrogen, because of its high electronegativity, is the very same thing. So go back to mechanisms dealing with aldehydes and ketones and esters and all of that stuff under acidic conditions. What was the first step? Protonate the carbonyl oxygen. What was the second step? Attack the carbonyl carbon with a nucleophile. What is it going to be here? Protonate the nitrile nitrogen and then attack the nitrile carbon with the nucleophile. The nucleophile in hydrolysis is water. So water comes in, attacks the nitrile carbon, but we can't stop there because if we stop there, we're going to end up with a carbon with 5 bonds, and that's no good. So that when we bring that water molecule in, we're going to have to chase away one of the bonds in this triple bond system, giving the electrons to nitrogen, which doesn't want to be positive. It wants to be neutral or wants to be negative. So after water attacks, we have a species that looks like that. Right, so this should all very much ring a bell. It's very, very similar to what happens when an aldehyde or a ketone or an ester or any kind of carbonyl compound reacts with acid and water. Okay, and so now what I see here is double, single bond to hydrogen. I see the tautomerizable unit. So I'm going to tautomerize this. Right, I'm not going to go through the mechanism of the tautomerization. We've done that already. I'm just going to apply the formalism of tautomerization. Double, single bond to hydrogen. The double bond and the single bond change places, and the hydrogen appears to jump from one end of the tautomerizable unit to the other. And so I have that. And this guy, this is the very same intermediate that we would get if we were to take an amide. If we were to take an amide and add acid to it, what would we get? The very same thing. And so these steps have led us into the acyl substitution realm of reactivity. So the rest of this mechanism is just acyl substitution, hydrolysis of an amide under acidic conditions. Okay, so I'm going to put this in brackets, right? Because this isn't happening here. This isn't happening here. I'm just trying to make the comparison about how this intermediate derived in this way is the very same intermediate that you would get if you started with an amide and added acid to it. Okay, and so now this guy, he's going to react with another molecule of water. He's going to react with another molecule of water, and this is just acyl substitution. Right, not going to go through the mechanism because we've done that plenty of times before. It's just acyl substitution. We end up with the carboxylic acid. There's the thing that's not carbon and not hydrogen on the carbonyl carbon. This functioned as a leaving group. It went away. The nucleophile minus a proton took its place, right? So that's just acyl substitution that we're used to. But now the problem, and to finish up this mechanism, the problem is this is a pretty good acid, that's a pretty good base. These two guys are going to do an acid-base reaction unless there is an acid stronger than this carboxylic acid in the reaction mixture. Something like HCl or something like sulfuric acid, right? All of those acids have a lower pKa. They have a negative pKa. pKa of a carboxylic acid is about 5. This is acidic, but it is a weak acid compared to something like sulfuric acid or nitric acid. So if we don't add extra acid, these guys are going to undergo an acid-base reaction. So what is done is that we add more acid. We have that H plus that I said was not a catalyst. We have that H plus and we feed it to this guy. H plus. And this guy would be from maybe HCl or from H2SO4 or from some other very strong acid. So I hope you understand what I'm trying to get to here. That's a base. This is an acid. If they are just left to their own devices, they're going to have an acid-base reaction that is going to destroy this carboxylic acid. We don't want this carboxylic acid destroyed. We're trying to use the Strecker synthesis. We're trying to create a carboxylic acid. So we need to bait this guy with something else. We need this guy who is a base. We need ammonia, which is a base, to react with an acid other than the carboxylic acid we're trying to preserve. So that's why we have to add this extra proton in that net equation I gave before. So we would add HCl or H2SO4 or something else to distract this ammonia from eating up, reacting, destroying this carboxylic acid in an acid-base reaction. Okay, so that's the chain of events for this hydrolysis of a nitrile under acidic conditions. So this stuff is new. Tautomerization, that's hardly new. Acyl substitution, that's hardly new as well. The nitrile can also be hydrolyzed in base. So let's go through that. So let's talk about base hydrolysis of the nitrile. All right, so under basic conditions, the overall reaction will be, there's our nitrile plus water. Hydrolysis means breaking with water, so that's the water. Under acidic conditions, we have H plus, but under basic conditions, we would have OH minus, right? That makes total sense. When we were talking about acids and bases, we pointed out that something like this would function as a base. So these are basic conditions. And we have to heat this up. The product is going to be not a carboxylic acid, but rather a carboxylate plus ammonia. Okay, so the nitrile can be hydrolyzed under acidic conditions. It can also react with water, hydrolysis under basic conditions. All right, so now let's look at the reaction mechanism here, and we'll see, we can tie this all back into acyl substitution. All right, so under basic conditions, there is no H plus. That was our first step under acidic conditions, protonate the nitrile nitrogen. Under basic conditions, there is no H plus. So we have to skip that first step, and so what happens immediately is attack of the nitrile carbon by the nucleophile. So these are the two things that are in the solution. Which one is the better nucleophile? Is water better nucleophile than OH minus? Oh, heck no, because a nucleophile is something that's electron rich. Who's more electron rich, neutral water or negatively charged OH minus? OH minus is a far more powerful nucleophile. So it's not water that is going to attack the nitrile carbon. It is going to be hydroxide. So hydroxide attacks the nitrile carbon. We can't stop there because if we do, we're going to have a carbon with 5 bonds. So what we have to do is chase away the one of these bonds in the triple bond, giving the electrons to the nitrogen. Okay, so we have an intermediate that is going to look like this. All right, and so now what a couple of different pathways could be followed here is that we could tautomerize, right? A double, single bond to hydrogen. So just like before, we could tautomerize. Where the double bond and the single bond have changed places, and the hydrogen has jumped from one end of the tautomerizable unit to the other end. But I had to be careful with the charges here. I know that nitrogen, when it forms 2 bonds, has a negative charge, so that's why I wrote N minus here. And we also have water present, and so water comes in. Water is whole. And so a molecule of water comes in. It protonates that negative charge on the nitrogen. And what we've created is an amide. Right, so this is very comparable to what we did before in the acid hydrolysis of the nitrile. Is that the reaction of the nitrile with water and acid, or the reaction of the nitrile with hydroxide and water, they all lead to an amide. And so the last steps of this mechanism are just going to be acyl substitution, basic conditions. That's the carbonyl carbon that's bonded to something that's not carbon, not hydrogen. Carbonyl carbon bonded to something that's not carbon, not hydrogen. This takes off, the nucleophile takes its place. But just like we said before, this is a carboxylic acid. This is a pretty good acid. This is a base. They're going to swap a proton. And so this leads to the carboxylate. Right? That was the step that we didn't want to happen in the previous, in the acid hydrolysis of the nitrile. But here it's going to, because we don't have any extra acid. We're not adding any extra acid. And so we get this carboxylate. Now, if we wanted to, we could take this carboxylate and in a separate step, we could add acid to it, and that would generate the carboxylic acid. If we wanted the carboxylic acid and not this carboxylate. So the nitrile is actually a masked carboxylic acid. And how do you take the mask off? Reaction with water and acid and heat. or reaction with water hydroxide and heat. So this is a way that the nitrile can be converted to a carboxylic acid. Okay, so that's all I have for you today. I do wish you good luck on your exam. Any questions or any discussion before we break? No? Okay, well, have a good day. The test will start at 8, right? Is that when it started last time? Okay, same logistics as last time, nothing new. What else? Okay, bye-bye, everybody. I guess. Anything else?